Bon matin, Hackfest! Hey, merci beaucoup d'être là. Thanks for being here. This week was crazy. So we're starting late. That's Hackfest. That's how it works. Fait qu'on est en retard, comme d'habitude. Cette année, 15e édition, donc édition évidemment spéciale, un nouvel endroit encore, nouveau difficulté à placer les choses en place. Donc c'est ça qui arrive. Ce que j'aimerais que vous regardiez, en fait, tous les plans que vous avez sur le petit pamphlet, la vraie horaire, c'est sur le site web. Fait que gênez-vous pas d'aller sur le site pour voir les dernières mises à jour. Donc, cette année, vous allez voir l'expérience Hackfest, c'est plus que des conférences. En fait, vous faites le tour de tout le building au complet. Il y a des villages de IoT, de social engineering, d'électronique, radio amateur. Il y en a pour tout le monde. Donc, voilà. Ce soir, et les deux soirs, on a du poker, poker table, du blackjack, des bars et tout dans la salle de CTF. Si vous ne faites pas le CTF, vous pouvez aller voir ça et vous amuser. Cette année, pour le Hackfest, si vous nous suivez, on est évidemment très impliqués dans la communauté. Puis la grande nouveauté, en fait, il y en a deux. Hier se tenait Polar, qui est l'événement pour les managers en cybersécurité. Donc, on a eu une centaine de personnes, des CISO, gestionnaires et tout, pour positionner la Hackfest au niveau autant gouvernance que technique comme ici au Hackfest. Mais la grosse nouveauté que vous irez voir dans le foyer 100 au bout, c'est les startups de cybersécurité. Donc, les startups, il y en a 12. Allez voir leurs produits. Intéressez-vous à ça pour investir localement. L'idée de la startup, c'est d'avoir de l'investissement au Québec qui est beaucoup meilleur que ce qu'on a aujourd'hui, de faire venir de l'argent de partout. C'est l'objectif dans les prochaines années. Donc, beaucoup d'efforts de la communauté comme ça, de l'équipe. Et voilà. Ce qui est intéressant à comprendre du Hackfest, c'est que notre équipe qui organise ça, on est 5 ou 6, ils sont ici un peu dans la salle. 6, merci, trop de bonheur. Et on a mis ça en place avec cette petite équipe-là, on est tous des volontaires, il n'y a personne qui fait un sou ici, donc c'est vraiment une communauté. Puis si vous n'êtes pas déjà là, la communauté de Hackfest est sur discord.hackfest.ca, il y a déjà plus de 4000 personnes. Impliquez-vous, partagez de l'information, discutez. La même chose avec notre podcast qui aura lieu ce soir. L'horaire a changé. Venez discuter avec nous pour, peu importe, tous les sujets de sécurité, hacking et opinion et autres. Cette année, on est dans le thème un peu Back to the Future. Pourquoi? C'est le retour vers post-pandémie, si on peut dire. Le retour vers les années 2018-2019 avec l'événement. L'année passée, on a réussi à faire 1000 personnes en 4 semaines, ce qui était impressionnant. Cette année, on retourne dans les chiffres de 2018-2019 avec presque 1400 à 1600 personnes. Donc, merci tout le monde d'être ici. Donc, j'espère que vous allez avoir un bon Hackfest. J'ai l'air un peu stressé matin, je ne suis pas d'habitude. Cette bande-là m'a organisé quelque chose, ça a l'air. Fait que je vais les laisser gérer ça. Merci tout le monde. Bon Hackfest.
Bonjour tout le monde. Hi everyone. My name is Simon. Je suis Simon. C'est moi le directeur de BSP Entertainment qui fournit des services de DJ et photo et plus depuis 14 ans pour le Hackfest cette année. Je voudrais inviter le staff de BSP à se joindre à moi. Pour l'occasion, on a décidé d'aller above and beyond. Patrick, join me. Join me. Come on. Yep. We decided to go above and beyond. So, since it's a Back to the Future theme, vu que c'est une thématique de retour vers le futur, on a décidé d'aller above and beyond. Just check it out.
Share the screen.
Connection issues. One, two, three, go.
Okay.
All right, let's press play. No sound. Sound. Who's at the sound at the back? Go. Yeah. No, no sound.
Hey everybody, it's Leah Thompson,
No.
aka
Non, il sort sur ton laptop.
Baines, McFly, Tannen. Hey everybody, it's Leah Thompson, aka Lorraine Baines, McFly, Tannen, McFly, Maggie McFly from Back to the Future. And I want to thank Patrick for making a Back to the Future theme party, and I hope everyone has a smashingly good time. Simon says that you're going to roast Patrick, so Patrick, don't take it personally. Whatever they say, it's all out of love, so don't take any of it personally. I hear the DJs are Back to the Future minded, so just drop a little hint. Maybe you should play Power of Love. I don't know. Yeah, I think you should. I hope you enjoy this unique moment in time and have a great time because, well, I love Back to the Future too. So thank you, Patrick, for being a fan of my work. Simon, thank you. And I hope all of you know that you are absolute dreamboats. And remember, if you put your mind to it, you can accomplish just anything, especially if you wear purple Calvin Klein underwear. Lots of love. Have fun. Party down. Everybody who's anybody drinks. Remember that, too.
We don't have purple Calvin Klein underwear to give to Pat, but at least we gave him the almanac. It's a good start. Good. Have a good fest, everyone. There you go. Well, woo, done deal.
Music. Can we put the music? Qui ça? Ils sont pas là? J'ai aucune idée, ils peuvent être où? On les a oubliés. OK. On va refermer les salles. Merci tout le monde. Comme j'ai dit, petit délai. Merci à tous d'être patients. L'horaire va être décalé d'un 15-20 minutes et on start ça. Y a-t-il quelqu'un qui veut faire un shot avec moi sur le stage? J'en ai besoin. Who want a shot? Come on. Really? Tu te comptes pas, tu bois tout le temps, toi. Hey! Je touche plus à rien. Who wants it?
Ben pas là, puis je pense qu'ils vont m'en donner un de toute façon tantôt.
Bon, FS?
On va en prendre un finalement.
Hey, pas de trouble.
C'est où?
Ici. Ouais. T'as ton micro à toi, right? T'as un micro.
Okay, looks like we're ready to start. So, as you understand from the way I'm speaking, it will be an English talk. I'm going to say a few words about the man you're about to hear. Simon Lacasse works as a pen tester at Desjardins with a focus on company-wide objective-oriented security tests. He has a strong interest with web application and infrastructure security with a background in software engineering. He enjoys making his own tools to solve the different problems at hand. When possible, he likes to give back to the community by making his tools public and open source. He is an alumni of the PolyHX Cybersecurity Club from Polytechnique, Montreal. Please give him a warm welcome to Simon Lacasse.
Hi, the sound works? Okay, cool. Yeah, we lost the screen, that's nice. Nice, what can I do? I'm plugged in. What? I guess, ouais. Non, c'est lui. Non, juste le micro. Ouais, mirror. Oh. Good. Nice. All right, so I've done nothing. All right, so welcome everyone to my presentation on weaponizing and auditing secret servers. I'm Simon. They already introduced me, so I'm just gonna skip this slide. As he mentioned, I worked for Desjardins, and I'm part of the adversary simulation and offensive security department. And I'm part of this sub-team called RUP for Reconnaissance and Operational Pen Tests. And as he mentioned, the main thing that we do is company-wide objective-oriented pen tests. So I'm just going to skip through the rest. I'm here today to talk about privileged access management solutions. So sometimes they're called secret servers or vaults. You'll see myself, I use the term secret servers a lot because I think it's a really telling name. But it does make for a lot of repetition of the term secret, but that's gonna, yeah. So they, of course, store all kinds of secrets, and they can be used by applications as well as users. They offer sometimes different other features than just storing secrets. Sometimes you can use them to rotate credentials, and you can use them to sometimes connect, the connect through capabilities, so to, let's say, connect through SSH. And of course, there are multiple vendors. So in general, the types of secrets that you may find in this secret server, well, you'll have these standard secrets that you would expect. So your usernames and passwords. You'd have your tokens and stuff like that, role IDs and secret IDs. This is specific to HashiCorp. We'll talk about that later. And you'll also find files. So sometimes you would have SSH keys, certificates, stuff like that. But in reality, you could have anything in there. If it helps with your deployment, you can put any file in the secret server and get it upon deployment. It works properly. So here on the screen, you have this example of HashiCorp secret. This is the AppServer01 secret in the AppServer01 folder in the KV secret engine. We'll talk a bit more about that later. So why would you use a secret server? Well, of course, it helps with secret management. So, but it helps in many different ways, right? So you can use it to identify secret owners. So if you have to rotate a credential, you're probably gonna have to notify the owner of this credential. And if all your credentials are stored in the same place, well, it helps greatly to identify whose secret it is. If it's only on the disk, you're gonna have a hard time knowing who's the owner of this secret. It also helps with your secret storage. So instead of storing it on your desktop or in Office 365 or in source code or stuff like that, your standard bad place to store your secret, then you can store it in the vault itself, and it helps having your secrets everywhere when they're all centralized in the same place. It helps with secret rotation as well. So when you want to change your secret, if everyone references this secret at the same place, it's easier to change it at this one spot than everywhere in every application that references the same secret. And it also helps with monitoring of your secret access. When someone logs into the secret server, you have a log there. When someone accesses the secret, even lists the secret sometimes, depending on the vendor, you'll have a log. So it really helps knowing who accessed the secret. If your secret is on the disk, you're not going to have this same logging experience. Why would you use, example PAM usage, sorry. So you have a couple different cases here, but in reality, there are as many cases as you want. So the first one that I saw myself is an application being given secret server credentials upon deployment and using it to get in real time the credentials that it needs to do its different connections. So maybe accessing a database or a third-party server or anything really. So this is the main case that I've seen. You also have these users that can have a lot of credentials to manage, and instead of using like a local key pass or a local vault on their computer, they can use this remote secret server. There's also the case of a team sharing credentials. Let's say for a test server, you have several testing accounts, and all these developers, they will share these credentials. You can share them through the secret server, and it helps maintaining them. And as I said, depending on the different features, you can use them as a connect-through platform. So my example of the SSH server, you may want to go through this PAM solution to connect through SSH. And at the end of this SSH session, well, first you'll have better logs. And at the end, you'll have this solution that may rotate the credential on the server or do the different stuff like that. So as an attacker, what's our use case? Well, what's interesting is not the secret server itself as much as it is the secrets inside the secret server. But to do that, to access those secrets, you have some prerequisites. So the first one being having access, like being able to log into this server. So to do that, you need to compromise different credentials. You may get user credentials some way, but you may also get application credentials. Now, you may get these credentials through remote code execution, memory dump potentially, if they're hard-coded in leak code, sorry. You also need to be able to reach a secret server on the network. So this is the other prerequisite. Obviously, to talk to the secret server, you need to be able to reach it through the network. So the use case that we'll use today for our demo, as well as our different examples, is basically an attacker connecting, like having remote code execution on this web server, stealing the credentials there, and being able to reach the secret server, obviously, through the remote code execution vulnerability. So all our examples today will be done with HashiCorp Vault in mind. So for that reason, we'll go through a little crash course on it, just to go through some features that are unique or proper to HashiCorp Vault. So first, when you deploy your HashiCorp Vault locally, you have to log in with the root user, but this is like the recovery user, so you don't want to use that. So then every user is going to have to log in with their username and password and stuff like that. So to do that, you have to enable the different authentication methods. So there are many authentication methods, but the first, like the main two that we're going to use today is your user pass authentication method, which is your standard username and password. And then you have this app role authentication method, which is basically the same as username and password, but instead of a username, you have a role ID, and instead of a password, you have a secret ID. But other than that, these two are UUIDs, but they're basically just complex username and passwords for an application instead of a user. The other thing that is important to know is that every secrets in HashiCorp Vault, they're stored in something called secret engines. There are many types of secret engines, so some of them are to be used with SSH and stuff like that, but the ones that we're interested into today for our use case is the key value secret engines, or KV for short. So there are two versions of these secret engines. There's KV version 1 and KV version 2. But they're roughly the same, the main difference being in the way that the data is stored in the API and how it's presented to the user. But other than that, it's the same idea behind it. You have this secret that then have these keys with these corresponding values. So let's say your username key with your value of the username, then your password key with your password value and stuff like that. The last thing that we need to know is that for HashiCorp Vault, the API doesn't really use IDs to get the secrets. It's fully path-based, actually. So when you're trying to reach a secret, you simply specify the secret's name in the path with its full unique path to get it, instead of specifying an ID like you would do in different APIs. So here you have this example of a path with the KV secret engine, and then this app server 01 folder, and this user 01 secret. So this is what it looks like in HashiCorp Vault. So back to our example, we have this app server 01 compromised web server. You get those credentials, and you're able to connect to the secret server. Now you use it, and you dump these 6 first secrets. So you then reuse these secrets again and reconnect to the secret server with the ones that are able to. And then you get even more secrets. And then you reuse these secrets again, and you get even more secrets. So what's the issue there? Well, this first account, this is a really small example that I gave you. This first account may get dozens and dozens of secrets. Now, those secrets, some of them, they may be files, but some of them may be credentials, but some of them may also be like tokens and stuff like that. So there's a lot of parsing and comparing things to do. And of these new credentials that you found, some of them may be used to connect to the secret server. They may have the privileges, but some of them may not. So you have to test all of them. And then of these new credentials that can connect to the secret server, some of them may be able to get new secrets, but some of them may not. And of these new secrets, well, some of them may actually be new, and this is a new value that you're interested in, but some of them may have access to the same value. But since you have dozens and dozens of secrets every time, it's really hard to do manually, and it's a lot of comparing, a lot of parsing, a lot of testing recursively these credentials on the secret server. It's really tedious, takes a lot of time, and it's really prone to errors. The other thing that's important to know for an application owner or developer is that you gave the proper access to your application. So when you're giving these initial secret server credential, you have like this level of access in mind that you're giving to your application. But if you, by mistake, give more credentials, not more credentials, but like credentials that can reconnect to the secret server, and that way you give out more credentials, then you're breaking like the least privilege principle, and it may have like great security repercussions, right? There are tools currently for an attacker to compromise secrets in a secret server, but they're mostly able to decrypt the local Vault files. So this is not a use case that happens often, right? If you compromise the secret server's backend, like the backend Windows or backend Linux, then you've already won, basically. Like it doesn't really happen often that you control this server, but it happens often that you compromise an application, or you found credentials on the server or on someone's desktop or in Confluence or whatever, and then you're able to connect to this secret server. This use case happens more than the other one. So the last thing is a lot of the logic between a lot of the logic of stealing secrets and reusing them on the secret server, then listing the secrets, then getting those secrets. This is all reusable between the different secret servers. So we're really in need of a proper tooling to do that. So for that reason, I created a tool called SSCrawl for secret server crawl. So what is it? It's a Python 3 CLI tool that recursively connects to the secret server, get all those secrets, all those credentials, reuses them, and it does that from an initial access. It has several features. It supports different vendors, so it's extensible. It supports the different authentication methods offered by the vendors. It recursively goes through the access tree, the secret access tree, which is what I call the secrets that you get when you're traversing the secret server. It's multi-threaded, so it helps with execution time. It supports different types of secrets that you may find, and it generates a graph for better presentation and better visualization of what you found and the issue when you're presenting to stakeholders. The current supported PAM vendors There's the Delinea secret server, which is formerly known as Tychotic. They recently changed name. And there's the HashiCorp Vault, HashiCorp Vault, which is well known. So the big issue to support different secret servers is that often they're not free, actually. It's a company product. So this is a big issue in supporting them, because I'm not going to pay for every tool. But as you can see, there's still a lot of work left. Here I listed 15 other vendors of secret servers, and there are many more, I'm sure. Obviously, some are bigger than others, but yeah, there's a lot of work left. So a word about the extensibility. So to support a new secret server, a new vendor, you have to extend the secret server class in the tool. So to do that, you have to override these 4 methods. So the first one being init, which is basically the constructor in Python. The next one is connect session, which is a login function. The next one is list secrets, which obviously lists secrets. And then you have get secrets threaded, which takes a list and then steal the secrets from the secret server. You also have to expose the different supported authentication method. This is because SScroll is going to tell you how it's trying to log in to this secret server. And it's going to give you more context too. So if it makes a difference how you logged in to get those secrets, SScroll is going to tell you how this account was logged in when trying to get the secrets. So if it makes a difference, you're going to have this context to be able to act differently. So here you have this example of HashiCorp with the user pass authentication method and app role authentication method, which are supported there and exposed through the authentication methods list. So to really go through how the tool works and how it steals secrets, we're going to go through this pseudocode here. Obviously, this is an overview of how it works. It's not the real code. The real code is a bit complex, a bit more complex. But yeah, we'll go through it and see how it works. So the first thing is the initial call. So at this point, you have all those CLI parameters that you passed at first. They're all parsed at this point. And you also instantiated the first, the proper secret server object. So if you're trying to work with HashiCorp, you have this HashiCorp secret server that is already instantiated at this point. And this is a call to the main recursive function that we're going to use throughout the execution. You have to pass the user-given username and password. So here it's user01 and password01. Password 1, sorry. The next step in our execution flow is the authentication. So for every authentication method available, SScroll is going to try to log in with it with the given credentials. And then if the login works, it's going to continue execution. And if it doesn't work, it's going to skip through the code and try the next authentication method. So why would you go through all these different authentication methods? Well, when you find credentials, like when the user gives you credentials, he can give you more context. But when you find credentials, if you have a username and a password, well, you have no way of knowing really if it works through LDAP, if it works through the local authentication, if it's an NTLM authentication. So for this reason, you have to go through them and try them all. And then the other reason is sometimes you could have the same username and password combination that is able to log into the secret server, but and it's able to log in several different authentication methods. And when you use these different authentication methods, you're going to get a different token that maybe has different permissions and access to different secrets. So it's still worth it to try them all and look for everything that you can find. So this login function, what it does, we just saw it's called actually connect session. This is the pseudocode. And this login function, what it does is it modifies a Python request session object to authenticate it. So what I mean by that, it's usually adding a session token to a header or a cookie, or this is basically how most login works. This function obviously returns true if the login is a success and false otherwise. And other than that, all the authentication methods, well, they're vendor specific. Some of them are the same, but some of them are different. So for the current supported PAM vendors authentications, we have here for the Delinea secret server, we have this standard local authentication that is supported. Then you have this LDAP or Active Directory authentication. Then NTLM, and if you support the NTLM authentication, well, might as well support pass the hash, right? And then for the HashiCorp Vault, you have this local authentication and then this app role authentication, which is application specific. I've only seen it in HashiCorp Vault yet. But you can see there are many authentication methods left. On this image, we have all the authentication methods available for the standard HashiCorp Vault. So some of them are more interesting than others, but there are authentication methods left to support. Then the next step in our execution flow is about listing secrets. So this also behaves differently from vendor to vendor, but HashiCorp is going to try to differentiate these different secrets by ID. So this method basically has to make an ID for its secret. So for some secret servers, you already have an ID naturally in the API. This is perfect. But for HashiCorp, you basically have to make your own IDs to be able to make it, since the API is fully path-based. So you can use these unique paths as the ID. It works perfectly. This function also returns a secret list item list. So these secret list items, they're basically an object for a unique ID, but you can extend it. So because this list is going to be passed to your getSecrets function. So if you need more context when you're trying to get a secret, you may want to extend this this class and add information that is relevant to you that will be relevant to you when you're trying to get the secrets. So here's an example of how it works with HashiCorp Vault, like getting secrets. So as I mentioned, there are secret engines in HashiCorp Vault. So you have these secret engines here that are listed. So you have to list them first, right? And then this one is not that interesting. These two are definitely not for our use case. So we'll focus on these three key value secret engines. We have this KV, legacy, and then secret. So if we basically click on the KV secret engine, we have here these three secrets. We have user02, and then these two secret folders, actually. They're not really secrets, AppServer01 and AppServer02. Now, if you click on the AppServer01 secret folder, then you have these secrets on the right that are listed, which is AppServer01, Cert01, so on and so forth. So what does it mean when you're listing secrets here in HashiCorp Vault? You need to recursively go through, well, first listing the secret engines, and then recursively go through all these secret folders to really list all the available secrets. So this is for HashiCorp Vault. For other secret engines, it may be much simpler. It may be only like a standard list with paging and stuff like that. The next step in our execution flow is getting the secrets. So this is a part that is really multi-threaded. This is obviously vendor specific. So as I mentioned, SScrawl is going to give you this list of IDs so that you built yourself to be able to reach and to get those secrets. It supports the different types of secrets, so these standard key value ones for username and password and stuff like that, and then the files that it downloads to the local disk. And yeah, it modifies this list of secrets as output. So this is how it outputs to the main execution flow. The last part of our execution flow is the recursivity. So for every new secret that is found, SScrawl is going to try to go through the flow all over again. It's going to call the getAllSecrets function with these new username and passwords. And that way, it's going to retry to log in with them. And if it works, it's going to retry listing secrets. And if it works, if you're able to list secrets, it's going to retry to get them and then go through it all over again, recall for all these new secrets this main function. So this is obviously what we call a recursive function. Every recursive function needs an exit condition. So the exit condition here is basically if you're not able to log in with any new credentials or you don't have any new secrets, then the flow is going to start exiting. So we're going to go through a little bit how SScrawl traverses the different secret access trees. So this is an example that I built. You have these AppServer01 secrets that are compromised, that we compromised ourselves and that we gave to the tool. So SScrawl uses breadth first search when it searches for secrets in the trees. So what it means is that it's going to list and get all the secrets that it has access to before going any deeper into the tree. So here with the app server 01, we're going to list all these 6 secrets in the second column before going any deeper. But then once it listed and got all those secrets, it's going to reuse this user 01 secret and connect to the secret server again. And then it's going to list this app server 03 and user 03 secrets before going any deeper. And then it's going to reuse this app server 03 and get these 3 new credentials. But of these credentials, they're either already found or either they're a file and are not really useful to connect to the secret server. So it's going to start returning at this point, and then it's going to use, it's going to go back there, and it's going to use this user 03 secret, connect there. We already found the user 01 secret. It's going to go back all the way, and then try to log in with this. This is a file, doesn't work. Go to this. This is database credential. It's not going to work to the secret server. This is a file also. Goes there. These credentials, they're able to connect. List these new secrets. User 02 is new and is able to connect. Lists SSH key 02. So this is how the tree is traversed by SScrawl. We'll talk a bit more about the multi-threading part of the tool. So by default, SScrawl uses 10 threads, but you can specify more or less with the -t or --threads parameter. The use case to specify more threads is obviously if you want to go faster, if you're finding too much secrets and you want it to go to take less time. But if you have like inconsistent results, you may want to slow down as well. So maybe specify only 1 thread. If you're running it and you have a lot of access denied, and you run it again and you have all those different access denied, like your permissions have changed, it's potentially that you're going a bit hard on your secret server and you want to slow down, then specify less threads. So how it works is that when it connects, it's single-threaded, since it's a small number of requests. And then when you're listing secrets, it's also a single-threaded, since this is also a small number of requests usually. And then it takes this list of secrets that it found, and it splits them between the n threads that you specified. And it uses then these little lists per thread to go and fetches all those secrets in parallel. So this is the part that's really multi-threaded. And this is the part that requires like hundreds of requests. Then on a single thread offline, it aggregates the found data, and then it goes through this whole flow all over again. To store the secrets, well, first we'll go how it stores files. So it downloads the files and stores them in the SScrawl files folder by default, but you can change the name with the -O or --out folder parameter. And every file that you find, every unique file will have a unique name, but every run, it's going to override this file since the name will be the same. So this has an advantage that it doesn't download like hundreds of files hundreds of times. So this is useful for that. But if you want to keep the difference between your runs, you're going to want to specify a different output folder. It also stores the found secrets, like every key value that it found, it's going to store it in a log file. So this log file is called sscrawl secrets.out, and it's by default located in the sscrawl files directory. Obviously, it's in a grippable format, so it helps you in consuming the data once you got it all. And then you can also change the name of the output file with the -O or --out parameter. As I mentioned, SScrawl also generates graphs for better visualization. So when it goes through the different access, it builds a secret server node tree, so or SS node in the code. And these SS nodes, they contain some information that is then useful to generate a graph that you can that is going to be generated if you specify the -G or --graph parameter. Now these graphs, they're all generated with the third-party software Plant2ML. So we'll go through a small crash course on how it works. Plant2ML is basically text-based graphing. So it has this custom language that you write in a text file, and then it generates a graph from there when you run the tool on the file. It has a lot of features, but SScrawl keeps it simple. So we only use 2 of those. We have these rectangles to generate the tree nodes. To specify a rectangle, you basically write simply rectangle and then the text that you want to write in this rectangle. Then you give it a unique ID. And if you want your rectangle to be of a special color instead of the default one, you can specify it in hexadecimal format at the end. The different links between these rectangles, they're specified with arrows. And to build a link between two rectangles, you simply have to write the first rectangle ID, and then this dash dash greater than, that is the small arrow, and then the second rectangle ID. So it's really simple to understand, and if you want to edit it by hand after, it's tedious, but you can do it, it's easy. To generate the graph, then there are multiple ways to do it. The one that I prefer is using the PlantUML Visual Studio Code extension. So this is going to generate an image in real time of your graph. And then you can copy-paste it in your report, or you can screenshot it, or stuff like that. But it's really convenient to work with. So this is what it looks like in Visual Studio Code when you're generating this graph. Like on the left, you have the text file, and on the right, you have this preview of what the graph looks like. And if you want to copy it, you can use this. And you can zoom in, zoom out, so it's really convenient to use. And there's also all this colored syntax that is really useful that is done by the plugin. If you don't want to use Visual Studio Code, there are other ways to generate the graph. So you can use the standard jar file and use it and generate the graph through the command line. You can also use this PlantUML public web server, but for our use case, I wouldn't use that if I were you, because you're leaking basically your secrets. So this is not recommended. And then if it's better for your use case, you can also deploy your own on-premises secrets PlantUML server. And either way, this is what it's going to look like. You're going to have this graph text at the top, and then it's going to be generated in the middle of your screen. But it's not as comfortable since you don't have this pretty syntax highlighting. So this is the same graph that we just saw. So it respects here the format of how SScroll is going to generate the graph. So you have first this start UML tag, which is mandatory, and then you have this bit of styling information. But then SScroll is going to print all the rectangles, so all the nodes at first, with their unique IDs. The first credentials that you gave, they're going to be shown as the root node, which is the start. And then here you can see all these other rectangles with sometimes they're colored. And then you have all these links between the rectangles. They're all here coming from the root node to these other rectangles. So once generated, this is what it looks like. So you have, as I mentioned, the root node on the left, and then all these other nodes on the right with the links between them. This graph is generated by me, actually, and is to show you the different color code that SScroll is using for you to go through the graphs faster, because as I mentioned, there's a lot of secrets that you can find, and it really helps to just go through them and have a little bit of color code to identify what the different types of secrets are. So this first one is the gray ones. They're your standard secrets. So these are secrets that SScroll understood, and they're basically a username and password combination. Then you have these green secrets, which are files. So they will be saved as such. And instead of having this username here in the node information, you're going to have the file name. Then you have the blue nodes, which are secrets that were already found. So these blue nodes, they're always leaves in the graph. And yeah, it means that you can basically find them somewhere else in the graph, like previously in the graph. They can either be gray ones, green ones, or orange one somewhere else in the graph. Then you have these red secrets, which are secrets that SScroll was able to list. So it saw that this secret exists, but when it tried to get it, it got access denied. So it shows it as such in the graph. And then you have this orange secret, which is a secret that SScroll was not able to identify and use it for its crawling. So it may be, let's say, a token, or if your username and password keys, they're in German, well, sscrawl is going to log them, but it's not going to know what to do with it because it doesn't understand that username in German is whatever. I don't speak German. So there are different ways to use sscrawl. So here are a couple different examples. We're still going to use our app server 01 example that is an app role account in an HashiCorp Vault. So this one is compromised. So if you want to use it, you have this username and password, which are UUIDs, since it's an app role. So to launch sscrawl, you obviously have to specify Python 3 and then the main sscrawl file. And then you have this -u parameter, which is a username. So here is the app server 01 role ID. And then you have this -p for password. And then this secret ID, which is also for app server 01, obviously. And then to know which type of secret server you're auditing, you have to specify it. So you specify it with the -- server, and then here it's HashiCorp. And then to know where, for sscrawl to know where is this secret server on the network, you have to specify the -- URL with the secret server URL. So this is to go through all of app server 01 secrets. If you wanted to go deeper and really go through the tree, you're going to have to specify the -- recursive parameter to go recursively through the different nodes. And then if you want a better visualization and you want to generate a graph, you're going to want to specify the -- graph parameter. So we'll go through a live demo. So bear with me. If it doesn't work, I have a video just in case. But it worked fine a couple different times. So I have these different secrets that are seeded in this HashiCorp Vault database on my VM. So if you can see here, this is from the screenshot. You have the key values, and then this secret that's here, and then this folder with all these different secrets, and this folder again, and then all these different engines. So if we just go and launch sscrawl, if we go with our, this is the first command that we saw, so Python sscrawl.py, and then the username, which is the role ID, and then the password with the secret ID, the server, and then this URL. So when you launch it like that, it's pretty fast, since it only got a couple of different secrets that I seeded myself. So it tried to log in with this initial secret ID, your role ID. So it tried every authentication method. So here it's trying user pass, and it got login failure. So then it tries app role, and then login success. So it listed then these 10 secrets, and it was able to log a total of 6 secrets. So it probably got 4 access denied there. So what does it look like? Here it generated this folder. So if we list the content, here there's this output file, and then these 2 files that it downloaded. So if we go ahead and read this output file, we're going to cat it. So we see all this content that it found in the secret server. These are the different secrets. If we want to get a bit more, because this is a small example, but usually you would have like hundreds of lines. So you're going to maybe look for the different usernames. So that way we see that we have this database 01 user and then user 01. So if we want to know more, because we want to connect to this database, we're going to, we're going to copy this related ID to the database 01, and we're going to cat for it. So, grep, but instead of that, we'll specify the ID. And that way we find every information about the database 01 user. We see that it connects to the database 01.local server with the database 01 password. So this is basically how you grep through the output file. If we want to go and look at the output of a downloaded file, we can go ahead and, let's say, read this config data, which is one of the files that we saw before. And basically what it does is just basically downloads the content to the disk. All right, so this is basically the first use case. If we want to go ahead and go with our other use case, I'm just going to go back there. If we want to go through the full extent of the access that it really has, we're going to want to go through this full access tree there. So you're going to specify the -- recursive parameter. And if you want to generate a graph, we're also going to specify the -- graph parameter. So when it recursively goes through the different secrets, it obviously tries to log in with the initial secrets again, but then it finds itself and it tries to log in again with itself because it doesn't yet have an ID for itself. It needs to find itself first, but it's only going to find the secrets that you already found. And then it retries every single credentials that it found, and it tries to connect with the different authentication methods. And that way, it's going to try to list all the secrets that it can. Since we also asked for it to generate a graph, we have this graph legend here that is conveniently printed to remind yourself of the meaning of the different colors. So what it looks like here, this is in Visual Studio Code. We have this, first this output file here that is much bigger. And then we have this graph that is generated by sscroll. So this is what we went through. This is the styling information and all those rectangles then right after. And then you have all these different links between the rectangles. And this is the end tag. So if we just generate the preview with this button here, obviously it doesn't work because this is a live demo. All right. So you have this graph right there. You have these initial credentials that you got. I don't know if it's big enough. Yeah, it's good. So you have these initial credentials. These are the app server 01 credentials that were provided. And then it listed all these 10 ones with the 4 access denied in red. And it reused then all these different credentials to reconnect to the secret server and see what are the different kinds of secrets that it can get and see if it can connect with them again and list even more secrets. So here, as I mentioned, it found itself. And since it didn't have an ID for itself yet because it didn't go through it, it retried to log in and it worked. And it was able to list secrets, but these are only secrets that were already found or access denied because it's the exact same account. Then you have these 2 files that were found. You have this database 01 credentials that we just saw, and these are not able to connect to the secret server because they're database credentials. And then you have this app server 02 that is able to connect, and it found this new user, which is user 02. And then this app server 02, it found itself, which we already found, so it's in blue. And then these DB02 credentials that it found also. And then it reused these user 02 credentials to list the other secrets, and so on and so forth. So that's how, basically, it ended up listing all the secrets contained in the database. This is because I seeded it myself, but otherwise, it finds as much secrets as it can. If we want to filter out this graph, because there's a lot of nodes here, it may not be exactly what you're looking for. So if we want to filter out this graph, well, we can first start by filtering out these blue nodes with the no already found flag. And we're going to go through the verbose output too, just to show. So when you specify the verbose output, you suddenly have these info nodes. These were already there, but you also have these new logs that are debug outputs. So first, sscroll is going to print you all the parameters that it's working with. This is just for convenience if you're debugging or if when you're using the tool, you're making sure that sscroll got what you gave it. And then it prints you more information on sometimes what failed. So here, this first account was not able to log in as user pass. And it tells you here in debug output, this is because it got 400 when it tried to log in. So this is probably it just doesn't work to log in with these credentials. Then it lists you this debug output. It was not able to access these 4 credentials. And then it also prints you more information about the secrets that it found. So here you have these secret IDs and then the different values that were found. If it's a file, you have the file name instead. And if it's a secret that was already found, it's going to print you as well. This secret, I found it, but I already got it, so this is not new. It also tells you sometimes if it makes no sense to try a login method. And a good example for that is for the app role authentication method. It's expecting a UUID as a username. So if it didn't get a UUID, then it's just going to skip the authentication method, and it tells you in the debug output as well. So this is what the verbose output looks like. If we go back to our graph and we go ahead and regenerate it, you'll see that all these blue nodes, they all disappeared. So this app server 01 that just had 6 blue nodes, here it only has these 4 reds. So all these leaf nodes that were already found, they're all hidden, and it makes for a much smaller graph. If you want to also hide these red ones, you can go for the no access denied flag. And if we just go and look into it, all these red nodes, they all disappeared, and the graph is much smaller. So here you can see app server 01 used to have 4 red nodes, and now it has nothing. If you want all the blue ones, but not the red ones, you can obviously just remove this first flag here, and you get this graph, which without the red nodes, but with the blue ones. So thank you. This was the demo. So if we go back to our presentation, we have on the right this final graph that we just saw with the blue nodes and not the red ones. And on the left, you have this graph that we saw throughout the presentation. So the graph on the left is basically the information that I seeded into the database. So when I started preparing for this presentation, I built this graph of what I wanted to show. And then I seeded this information in HashiCorp Vault. And on the right, you have the graph that SScroll generated. So you can see it's basically the same. Here you have app server 01. So these are the credentials that you seeded. And then here it found itself. So you can see here that it found itself. But then the tool relogs in because it doesn't have an ID for it yet. And it finds all these nodes. So this is the part that is different. Here it's not shown on this graph. But other than that, like the user 01 is right there. And it has access to this app server 03 and user 03 there. And these 3 credentials are there, and with this one being here also. So this graph generated is basically the same as what I seeded in the database, so we can see that it works. There are limitations to the tool, obviously. You have first to be able to reconnect with a username and password, you need to be able to identify that the information that you just found is a username and password. And these keys for the values, they're not always really standard, so this maybe make it sometimes hard to identify that it's a username or a password. So sometimes it's not going to try it to log in, but it's going to show it in orange in the graph. So you probably should look into it yourself, investigate a little bit, and see that, well, this is a username in German and password in German. Well, obviously, you're going to want to retry and relaunch the tool by hand and see if you can get any further in the tree like that. The other limitation is that this is not a red teaming tool. It's not a tool that tries to be discrete. It actually tries to be fast, and it's really loud. Makes a lot of authentications requests, a lot of authentication failures, and it gets the secrets as fast as it can. And obviously, to implement the other PAM solutions, you need to have access to them. So this is the other limitation. They're often not free. And when they are, well, they take a lot of time to configure because first you have to learn how to manage this PAM solution before you can really try to implement it. If you're a blue teamer or more on the defense team and you're trying to protect yourself against such technique, well, the first recommendation that I will have for you is basically that you segment your PAM solution as much as possible. Now, it's not always possible to micro-segment it, but that would be even better. But respecting the least privilege principle on the network is always a good thing to do. You should also audit your own secrets to know if they can access more than what you intended. So maybe use SScroll on your own time and try to see if it can go any further and build a tree of credentials that you didn't know that you gave to your application. And you should already be doing that, but you should monitor the secret server logs since this is a really important part of your infrastructure. And yeah, you should look to detect SScroll. You should look for an abnormal number of requests because, as I mentioned, an application should not be getting like 200 different secrets in a span of maybe a couple seconds. You should also look for an abnormal number of login attempts, and even better, the login failures, since SScroll tries all the different login methods available that it supports. It's really noisy on that part. So thank you very much for listening. If you want to get the tool, it's going to be available in a couple minutes on my GitHub on SScroll, so you can get the link basically using the QR code. And if you want to connect, well, you can reach out on LinkedIn. Thank you very much.